Section 3.6 talks about the chain rule. So here we're trying to take a derivative of a function within another function. I'm missing a parenthesis right there. There we go. Okay, much better. So a function within a function. This right here is an embedded function. That's when you take the composition of f composite g. The derivative turns out to be f prime of g of x times g prime of x, hence where the name chain comes from. Now, to better understand this, this is what we do. Whenever we have a function embedded with another function, like right here, you notice here we have 3x minus 2 embedded within the function x to the 6th. Here you have the sine of x embedded within x to the 5th. So if we try to separate them by using Leibniz notation for a derivative, dy dx, so Leibniz viewed this as two individual values. He said if you have two functions embedded within each other, like we're going to have in this section, what you do, you let u equal the inside function. So inside of a power function, the inside of a radical, the whatever you take in the log of, denominator of a fraction, the exponent of an exponential, and so on and so forth, the angle of a trig function. So you let u equal g. So initially I'm given the equation y equal f of x, or f of, I should say, g of x. So what he said, well, look, let this be u. If you take this and you let it be u, that means your y now is a function of u. And then he said, well, look, if you take a derivative of y with respect to u, well, guess what? Derivative of y with respect to x, that's normally what we do. Dy dx, he said, well, look, u now is a function of u. Take dy with respect to u, and here comes the chain rule. Whatever this is, and the derivative of u, look at u, and isn't u a function of x? Now, you could always cancel those and end up with dy dx any stage of the game. And that's what this is. So the idea is to let u equal a portion. In this case, the inside of a power function, the inside of a radical. So here we're going to let u equal the inside of this function, which is 3x minus 2. That means y have just became u to the 6. So basically, this is what I let u equal. Take this and put it in, and I end up with that. Now, why is this important? Because I know how to take a derivative of u to the 6, and I know how to take a derivative of 3x minus 2. Well, the way it works, if I take dy dx, well, y doesn't depend on x anymore. Y depends on u, and by the chain rule, u depend on x. Again, I could cancel those anytime, and by doing so, what's the derivative of y with respect to u? Well, that's 6u to the 5th. And what's the derivative of u with respect to x? The derivative of this with respect to x is a 3. And all what you have to do is come back and substitute back what u was, and you're done. And u was, and that would be the 3x minus 2. And there's the derivative. Initially, I didn't know how to take a derivative of this, but now I do. And if I apply that to the second problem, again, whenever you see two functions embedded within each other, well, you're going to let u equal. Now keep in mind that this is actually, let me just move that. This is actually the sine of x to the fifth power. So what's the inside? This is the insidemost function. I'm going to let that be sine of x. That means now y equals, and whatever we took out, there it is. And now when I say find the derivative of y with respect to x, you say, well, now y depends on u. And by the chain rule, this should match. And u depend on x. So dy dx is actually, well, let's see, what's the derivative of a power function? Bring the power down, subtract 1 from the power. And dy dx, the derivative of this with respect to x is simply the cosine of x. And all what I have to do is, at the last stage, come back and substitute back what u was. And u was a sine of x. And again, initially I did not take a derivative of this, but with the chain rule now I could do it. I'm going to do two more and kind of try to figure out what they're doing. If I let u be the inside, again, I not take a derivative of each of those, but not embedded. If I let u equal the secant of x, then y would become the tangent of u. Well, when I say find dy dx, you would say y now depends on u, and automatically those have to match again. U depend on x, and the derivative of tangent, we know that's secant squared of u, and derivative of u with respect to x is secant of x tan of x. And all what I have to do is substitute this back, and pretty much I'm set. So my answer would be the secant squared of the secant of x times the secant of times tangent of x, and there it is. Now when I get to the next problem, I'm gonna let u equal the inside. Well, again, this is the cotan of x squared, so the inside of the power function is the cotan of x. That makes y u squared. Dy dx is y depend on u and u depend on x. That is simply 2u, and the derivative of that is negative cosecant squared of x. Okay, that looks really bad. There we go. And then get u back, and u was the cotan of x. Now, if I really pay attention to what's happening, if I look back, it seems this is like looking at the outsidemost function is a power function. I brought the power down, subtract 1 from the power, times the derivative of the inside. And that's really what this was saying. If you have f of g of x, take a derivative of the outsidemost function times the derivative of the inside. If you look here, this was sine of x to the fifth power. Bring the power down, subtract 1 from the power, that's this part, times the derivative of the inside, which is the cosine. Again, if you look at this, the outsidemost function that we see is the tangent. Derivative of tangent is secant squared of whatever that is, times the derivative of that, which is secant tangent. Here, it seems we're looking at a cotangent of x squared. The outsidemost function is a square. Bring the power down, subtract 1 from the power, there it is, times the derivative of the inside, which is cosecant squared. Now, the hope is that in the long run, you could start using the new analogy, but if you have to write u equal every time, it's not that bad. So let's try it. if I want to take a derivative of this with respect to x, the outsidemost function is a 4. Well, bring the power down, subtract 1 from the power of whatever that is, times the derivative of that, which is 6x plus 3. And if you're not seeing it, let's do it. Let u equal 3x squared plus 3x minus 1. That means y equal u to the 4th. And when I say find dy dx, you would say find the derivative of y with respect to u and derivative of u with respect to x. And that would be 4u cubed times the derivative of this, which is 6x plus 3. And if you substitute u back in, that's 3x squared plus 3x and a minus 1. But of course, this is a lot quicker. But if you have a hard time with this, start working out the long way until you figure this out. Now, if I rewrite this, this is y equal, and I could say this is the sine of x to the negative 2 power, because I move this up. And when I say what's dy dx, the outsidemost function is a power function. Bring the power down, subtract 1 from the power, times the derivative of the inside, which is the cosine of x. And that would equal negative twice cosine of x over sine cubed of x. And that's the famous chain rule. Here's the idea though, or here's the deal. Now that you know about this, you're going to see it all over the place. So here we have the product rule. If I say find dy dx, well, derivative of the first is 2x times the second plus the first times derivative of the second. Well, the second, if you look closely, the second is actually, this is really x squared times the cosine of x to the 4th. So the second, you bring the power down, subtract 1 from the power, times the derivative of the inside, which is negative the sine of x. And there it is. Dy dx would be twice x cosine to the 4th of x minus 4x squared, the cosine cubed of x sine of x. And if I want to look at 236, I notice that inside is this, but it seems I have too many things to deal with. Let me do this the long way. The reason of that, I'm going to let u equal this angle. That's not an x. And I'm going to let w equal six plus secant of u, and that means y must be the square root of w. So here I had to do this 3 times. And when I say find the derivative of y with respect to x, you say now y depends on w. And again, w automatically they have to match. W depend on u, and u depend on x. So not twice the pleasure, 3 times. And again, I could cancel those and those. Well, that equals, what's the derivative of a square root? We agreed you're going to memorize that. That's 1 over twice the square root of w. Or you could write that as w to the 1/2, bring the power down, subtract 1 from the power. Now, what is the w du? What's the derivative of this with respect to u? Well, that's a 0. That is secant of u tan of u times the derivative of u with respect to x, that's 2 pi x. So altogether, I'm looking at 1 over twice the square root. What was W? W was 6 plus secant of U. And I know what U is. U was the angle, pi x squared, times secant of U. Well, what's U? We said U was pi x squared, tangent of pi x squared multiplied by 2 pi x. And of course, you could clean that up a bit. The 2's cancel out, and so on and so forth. But there it is. So that's chain rule. You want to get used to how that works. If I look at this problem, it says y equal f of x quantity cubed. Find dy dx. Well, dy dx would be what? Bring the power down, subtract 1 from the power, times the derivative of the inside, which is f prime of x. So now if I evaluate everything at 1, right, this would be a 10, 3 times f of 1 squared times f prime at 1. Well, let's fill in the blanks. That's a 10 we already know. F of 1 is what I'm looking for. And f prime of 1 is given to be f4. So if I isolate this by itself and they're all multiplied, yeah, that's 12. So if I divide by 12 both sides, I'll get 5 over 6 equal f of 1 squared. And to get f of 1, you simply square root both sides. And that should be plus or minus, unless they specify that it's positive, but they didn't. So every time you square root both sides of an equation, you pick up the plus or minus. All right, and yeah, that's the last thing we do. How about this? What is that? Given h equal, oh, I forgot to copy directions, didn't I? Okay, well, they want us to take the derivative at a. They want us to take h prime at 0. Well, isn't this a composite? You take the derivative of the outsidemost function times the derivative of the inside. And this is the derivative at x. If you plug 0 in, that's g prime of f of 0 times f prime of 0. And let's see what that is. H prime of 0 is g prime. Now let's see, what's f of 0? There is x equals 0. And f is right there, that's a 2. And at 0, what's f prime? F prime is a 5. And now this is saying what? G prime at 2. Now you are at 2. What's G prime? G prime is a negative 1. And that's a negative 5. How about this problem? Well, here we're taking h prime. The outsidemost function is the square. You bring the power down, subtract 1 from the power. Then you take a derivative of the inside, that's the quotient rule. It's going to be over the denominator squared. And then it's going to be derivative of the top times the denominator minus the top times derivative of the denominator. And if I evaluate all of that at 3, I'm looking at twice f of 3 divided by g of 3 times times f prime of 3 g of 3 minus, so wherever you see an x, plug in a 3. Okay, and what would this be? Okay, I need f of 3 and f of 3. I need f of 3 right there and f of 3 right there. What's f of 3? When x equals 3, f is right there, so it's a 3. So it's a matter of quantities, nothing more. Now what? Now I'm looking for g of 3. And there. What is g of 3? Well, let's see. When x equals 3, g is a 2. And then I'm looking for f prime at 3. And I also need g prime of 3. Well, f prime of 3 at x equals 3, f prime is a negative 3. And g prime of 3 at 3, g prime would also be a 3. And you simply multiply this and figure out what that equals, and you're done. That will equal, the 2's cancel out, that's a 3 times, and let's see. The denominator is a 4. Negative 6 minus 9, that would be negative 15 over 4. So altogether, negative 45 over 4. And here, I'd like to find the derivative of h at 2. Well, we do the same thing. That is, first we take a derivative, and I see a power function, bring the power down, subtract 1 from the power, times the derivative of the inside, which is g prime of x. Now if I evaluate that at 2, that's 3 times 1 plus g of 2 squared times g prime of 2. H prime of 2 will equal 3 into 1 plus. So if I'm looking for x equal 2, I need g of 2. There's x equal 2. And g happened to be right there, which is a 1. And I need g prime of 2. I'm still looking at 2, but now I want g prime, and g prime is right there. That will be g prime of 2, it's a negative 1. And I'm looking at 3 into 1 plus 1, 2 squared times negative 1. That will be a negative 12. And there's your homework in this section.